Welcome to our smart classroom. Today we'll explore molecular structures. Let's look at these models to understand the concepts better.
Welcome to the chemistry class. Today we are going to talk about the two topics, Bohr's Atomic Model and followed by Heisenberg Uncertainty Principle. Here I'm going to talk about only the fundamental truth. I'm not going to talk about the derivations of the Bohr's model, energy, radius, and velocity, just the what exactly in the theoretical way. And after this video, you can see the visualization of those Heisenberg Uncertainty Principle. Let's see. Before Heisenberg Uncertainty Principles, most of the scientists have believed that our Electron is a tiny planet, which means what? The planet which is revolving around the sun. So which means that the planet momentum and velocity exact, momentum and position exactly they can determine. The same logic is applied in the Bohr's Atomic Model. So which means what? You can see in the picture backside, where exactly orbit having is measured in values 1, 2, 3, 4, 5, right? Orbit red. So in the electron present in the particular orbit, we can find the exact position, exact momentum, 7 days. Right? Now, let me ask one question before we're into the next question. Can we identify the electron exactly? Can you see electron directly? Definitely no. So how we can see an electron? Definitely, I can say that you can pass the light. Means what? Light comes with a tiny particle package that we can call it as photon. So if I pass the photon towards an electron, I can see it. So here is the come to the picture. Completely the scenario is going to be changed. And so what actually happened here? When you pass the high amount of photons towards an electron, definitely we can see exactly position, right? But there is a change in the momentum. Why? Because the photon, that means light, it transfers the energy and momentum to the electron. Okay, if it is what happens if send the low energy of the photon. If she pass the low energy of the photon, electron's position accuracy will be low and momentum be high. So based on this concept, Heisenberg given mathematical approach, whereas delta x into delta p greater than or equal to h by 4p. What is x here? Uncertainty in position, where delta p means uncertainty momentum, and hm4 and pi values are the constant. So what exactly I can be doing? Can I say Bohr is a failure? Don't call it as a failure. But what I can assume? It is not a scientist failure. It is not our microscope is a vehicle. It is a fundamental law of the nature. That's all. So, for what Heisenberg density give the clarity needs, according to both, orbit is a fixed. But yeah, Heisenberg, you replace the orbit with an orbital. Orbital's electron cloud, where the electron can find out. So it is a quantum model. So that quantum model, electron cloud, based on that he can determine. So what exactly I wanted to see compared with the Bohr and Heisenberg. Exact position, exact momentum cannot be determined simultaneously. But where in the case of Bohr, exactly determined simultaneously. So Bohr isn't successfully expand the first atomic model. But Heisenberg Uncertainty Principle is given the the concept. There is a major difference, is a novel is a failure. So that's what I wanted to say. And the remaining the simulations or understanding visualization you can see in the my next topic.
Theory helps us understand. Visualization helps us imagine. Now, let's explore this concept in a more intuitive way. The principal quantum number, represented by n, tells us the main energy level or shell of an electron in an atom.
The maximum number of electrons that can occupy a shell is given by the formula 2n squared. For n equals 1, the shell holds 2 electrons. The radius of an orbit in the Bohr model is given by the formula r sub n equals n squared a naught. Here, a naught is 0.
Notice how the orbit radius increases as n increases. This directly correlates with the rise in energy shown here.
Although Bohr's model was revolutionary, it has certain limitations. First, it works only for hydrogen and
Scientists once believed electrons move in fixed paths, just like planets around the sun.
But a simple question changed everything. How do we actually know where an electron is?
In darkness, we need light to see a mosquito. Likewise, to detect an electron, we must use light. To locate an electron, we must interact with it. But the act of observation, the more precisely we determine its position, the moment we observe the electron, the photon collides with it. Observation itself changes the particle's motion.
What?
An electron is too small to see directly. To find it, we must shine light on it. Every observation requires a photon to interact with the electron.
Because both values cannot be known exactly, electrons are described by probability clouds rather than fixed paths.
Use gentle light and the electron remains undisturbed, but its position becomes unclear. Use powerful light.
Fixed orbits disappear. Electrons exist as probability clouds around the nucleus. Scientists discovered a surprising truth. The more accurately we determine where a tiny particle is located, the less certain we become about its motion. This is not a problem with our instruments.